When people talk about energy metabolism, you often hear glycolysis, the Krebs cycle, and the electron transport chain, but an important process most people don't hear about in energy metabolism is the conversion of pyruvate into acetyl-CoA, which occurs on a molecular machine known as the PDC. Don't worry if a lot of these words don't make sense. I'm about to give a brief overview of what energy metabolism is and where PDC fits into all of this. First off, the process which I'm about to describe specifically pertains to aerobic respiration, the most efficient form of energy production which requires oxygen. After gobbling your food, your stomach acids digest your food into component molecules, which are absorbed into the bloodstream via the small intestines and distributed to the rest of the cells in your body. These component molecules are crucial to the formation of ATP, the main source of energy for your body. The molecule we care about for energy metabolism is glucose, a simple sugar. Glucose is converted into pyruvate via glycolysis in the cytosol of the cell. Pyruvate is then taken into the mitochondria for further processing. First, pyruvate is converted by the PDC into acetyl-CoA. I'll come back to talk about this in detail in a bit. The acetyl-CoA is then taken into the Krebs cycle and turned into CO2 as a waste product to be released when you exhale. All along the way, NADH and FADH, two molecules known as cofactors, are created as byproducts of these processes. These cofactors are finally taken into the electron transport chain in the mitochondria to give electrons to oxygen, which creates H2O as a waste product. This process of transferring electrons to oxygen is what creates the majority of ATP used in your body. Now that you know where the PDC fits into energy metabolism, let's go into how it works. The PDC is a large complex comprised of three separate enzymes bound to each other. The shorthand for these enzymes are E1, E2, and E3. Pyruvate interacts with E1 where a molecule known as TPP cleaves or removes the CO2 from pyruvate. The pyruvate then becomes an acetyl group and forms a bond with TPP. This intermediate molecule is known as a hydroxyethyl TPP. Next in E2, a molecule known as lipoamide reacts with the acetyl TPP molecule and removes the acetyl group from TPP. This happens because the lipoamide has something known as a disulfide bridge, which is highly reactive. The disulfide bridge is what reacts with the TPP-bound acetyl group and transfers it to the lipoamide, forming a thioester bond. These bonds are high in energy, and they are the same bonds used in acetyl-CoA. The lipoamide then swings around and brings the acetyl group to a CoA-SH. The thioester bond is then transferred to the CoA-SH, and acetyl-CoA is formed. We have our desired molecule, but we're not quite done yet. Finally, we move over to E3. E3's job is to reset the rest of the PDC so that it can work on its next pyruvate. Bound to E3 is an FAD. This FAD resets the lipoamide group from before so that the disulfide bridge is reformed, allowing for it to form another thioester bond with another acetyl group. The FAD becomes FADH. The FADH is then returned to an FAD by a nearby floating NAD, which then becomes NADH. The NADH then floats off to where it is needed in the mitochondria. Now the PDC is reset and we have our acetyl-CoA molecule. This was a basic overview of how the PDC works and how it fits into the bigger picture of energy metabolism.